video for class 10, dynamics. And we're looking at the kinetics of particles, impulse, and momentum. So this is our introduction to impulse and momentum. I believe this is section 13.3 in the book. So the concept of an impulse, sort of like we already know, kind of what that is a very short duration force, right? So it's force times time. Most of the time it's short. It doesn't have to be short, but it's force times time. That's what an impulse is. And momentum, we probably already have a sense of what that is. We kind of really already kind of defined it. It's mass times velocity. As I've said before sometimes, it's like momentum is like, I think of as like a van, right? Where we got to push a van and we got to start it. We got to push it, and then it starts to roll, and it starts to roll, and now it's got momentum. And if you want to stop it, you got to run around to the other side and then push it back, right? And that amount of time that you're pushing it, that's the impulse. The force times that time, that's the impulse, and that causes momentum, right? So impulse and momentum are related in a similar manner that we did with work and energy. We have the momentum at the beginning, something happens to it, some impulse, and then we have the momentum afterwards, right? So we have a beginning state, something happens to it, and an end state. One of the big differences between work and energy and impulse and momentum is that impulse and momentum are vectors, whereas work and energy, they're scalars, right? So we actually have directions, so we can break the impulse momentum equations into components. So that's like an important thing. So let me switch over to my document camera, and let's take a look at what I would generally do for my notes here. All right, so we recall that we said Newton's second law is F equals ma, but actually says the sum of the force is equal to the time rate change of momentum, right? So that's that momentum that's right in there. That's equals F equals ma. So, we have introduced this capital L as a variable for a thing called momentum, and we see that the dotting that turns it into a force. But if we were to rearrange this equation right up here, right, we could say that we had sum of the forces right here times dt is equal to mass times dv. So we could stick some integrals onto the front of this right here, right? And mass being constant right here, we could now just rearrange the thing, and we could say, well, this is going to go from time 1 to time 2 and velocity 1 to velocity 2. So we could say, and without solving what this is right here, we just keep that as a thing, right? Because as I briefly mentioned, or as I alluded to, a lot of times the time is really short. I mean, it might be a large force over a very short amount of time. So we want to try, a lot of times we want to integrate it if we have that type of relationship, but we also might just want to keep it as a thing, and we'll call it impulse as an actual variable, a standalone thing. Right, so here is our main equation rewritten out. And mass times velocity 2 right there. So we say the beginning, see momentum before, mom before, mom after. And sometimes we'll even call this imp right there. And we might even write that down as a vector. Whoops. Might even write that down as a vector. And so sometimes you'll see it get written that way. We'll say this thing as an imp right here. We'll just call it an imp because right here we have this short duration impulse, right? Where Wormy is going to get hit by a baseball bat. And that time, that resonance time, when the bat is touching the apple right there, that's a very brief duration, but that is where the impulse is taking place. And it would be very hard to measure that accurately. I mean, we could do it with a high-speed camera, and you often will see that with like golf balls and that kind of thing, where you can actually capture if you have a fast enough speed, you could actually see that the golf ball is on the face of the golf club for a good long time. So what we do when we try to do this calculation right here, we write these 3 diagrams. So we have another 3 diagram method. 3 diagrams. And we have this like here, and I usually write, sometimes I'll write before impulse and then after. And you can see in here that the impulse might have a direction onto that. So breaking these things down as, here's the equation below as a vector, and I'll just put this as an impulse between 1 and 2. It's going to be equal to mass times velocity 2, right there. We have an x component and a y component. So we say x1 plus, and we might break this into the x component of its force. It's going to equal to mass times velocity in the x direction 2, mass times velocity in the y direction 1, plus the integral of that d, the force in the y direction, dt, and then this right there. So we break it into components. Something I forgot to mention up here, there might be some type of relationship that we might find between the forces and time. We might have some way of knowing it right there. But most often we might say, well, we could take the average of force in a particular direction and then times the delta t. We might say that right there, right? Or we might just keep it as one thing. All right, so let's see, what else do I have as part of this section here? Do I have anything else? The units. That's an important thing to discuss, right? So the units of impulse, what are they going to be? Well, they're a Newton second or a pound second. And sometimes I'll put a little dot in there, but that doesn't mean a dot product. I'm just trying to separate the two variables out. Note that we might have you might have momentum right here. Remember, like let's say in SI units, you'd have momentum as a kilogram and then meter per second right here. Well, notice that what we could do here is we could turn it into a kilogram meter per second squared times second right here. And that right there is a Newton, right? So that's a Newton second. So here it is as momentum. Here it is as impulse, right there. Some things that we might forget. Okay, so I already said if the force is constant, we could say it's the force times delta t. Also note that sometimes this is such a large value right here that we might ignore something like the weight. Right, the weight might be because the time that this is happening is so very small, and then the force is also predictably large, that the weight doesn't really matter all that much. So just be aware that sometimes we might want to put those things together. Now, when there is no impulse, we have what's the conservation of momentum, right? The conservation of linear momentum. And the reason why we're making this distinction is there's also angular momentum that we will talk about and discuss. That's going to be rotational things, right? So in a sense. So be aware that what we were saying, linear momentum. And if there's no external influences, we can say that it is a conservation. Or if we define what we're working on, and instead of just an individual particle, we could have a system of particles. And when that happens, we will have an equal and opposite impulse. And so it cancels out. So how we define the system that we're working on can turn it into a conservation of momentum, because what's happening here is that impulse is not external, it's an internal thing, and it'll cancel out, right? So I think, and we could say right here, we could say that now MVA1 plus MV, and this is to be A, it depends on they could be different masses here. is going to be equal to m. And sometimes we'll use this prime thing instead of 1. So I didn't do that here. The book does that quite often. They'll say, like, I kind of prefer to get the numbers in there because the prime starts to be confusing. But what they mean is it's the second event. So just be aware that you will see that sometimes. But I like to have, like, the numbering of the things, especially because there could be multiple things that are taking place, multiple stages that are taking place. So you might, like, we might take a bouncing ball and we might bounce it and then see what happens right there. So that the initial is 1, the second velocity is 2, but then now what if we're going to bounce again? I don't want to start using primes and primes and primes. So I think that's it. And then we want to do examples. Okay, so I'll do that in a different video. That was my introduction video. It's 11 minutes long.